All right. So in the last lecture, we talked about the impulse momentum theorem. And we talked about the conservation of momentum, introduced both of those ideas. Now here, I just want to talk about inelastic collisions and do some examples. I feel like last lecture was pretty theory heavy, and I think I only did like one example. So I don't want to leave you guys hanging. I want to make sure that you get a couple of examples that'll be useful as you work on problem sets. So let's move into just a quick review example of what we talked about in the last lecture. Um, Again, straight from your textbook. It does have good examples, and I do encourage you to read through those when you can. So we have a 10-gram ball and a 30-gram ball placed in a tube with a massless compressed spring between them. Okay. When the spring is released, the 10-gram ball flies out of the tube at a speed of 6 meters per second. What speed does the 30-gram ball emerge from the other end? All right. So let's think about how we can model this. Okay, so let's define the system to be the two balls in this tube. Okay, so the two balls are the system. You can see in our figure down here, we've defined that. We've drawn the system. Okay, now let's think about the forces we got. So the balls interact with each other. Okay, so we have interactions with each other. But you'll remember from last lecture, interactions within a system should all cancel out, action-reaction pairs kind of thing. Okay, in this case, the system is isolated because, now let's think about the external forces. Okay, we know that the ones inside my red circle here, they cancel out. But let's think about this. We have the upward normal force of the tube on the balls. Okay, so we have the upward normal force. And this is for both the normal force on ball 1 and the normal force on ball 2. They're both there. I'm just going to draw one vector though. Okay, so we have the upward normal force. We also have the downward force due to gravity on both of them. Okay. Well, it turns out since these balls are not accelerating up or down, we know that some of the forces here in the y direction is going to be the normal force up minus the force due to gravity down. There's no acceleration, so it's an equilibrium, 0 newtons. Checks out. Okay. So the net force equals 0. Now remember, and I'm going to make a note up here, that in an isolated system, the change in momentum over time is 0 if the sum of the forces also equals 0. So we do have an isolated system. The change in the momentum over time is 0. The momentum is conserved. Forces are 0. All is well and good. Looks like we'll have a pretty easy problem. All right, so let's run through the math here. So let's see, what are we trying to figure out again? Yes, what's the speed of the 30-gram ball after the spring is released and it sends both balls in two different directions, okay? So the system is still the same. We still have this system of both balls. It's just that all the momentum in there needs to equal 0. All the momentum has to cancel out. Okay, so we have our masses, we have our velocity of one of them. We just need to know the velocity of the other. Okay, so let's think about the initial momentum. Okay, so since the balls are initially at rest, well, that initial momentum equals 0. And since this is an isolated system, we've talked about that. Since this is an isolated system, what we start with has to equal what we finish with. So that means since our initial momentum is 0, so this is our start, what we finish with, our final momentum also has to be 0. Okay. Now let's add these momenta up. So we have the initial momentum of P1 plus the initial momenta of P2. We can totally add those up. This is our total momentum. So this is our initial total momentum, and this has to equal, we know what we start with, has to equal what we finish with. So here's our final momenta for each object. So we still have ball 1, ball 2, and of course, this has to equal 0, this has to equal 0. Both of these equal 0. Okay, I'm going to erase some of these notes. Oops, let's go back to green. Okay, so since the initial velocities are 0, okay, so we know since these balls are initially at rest, we know that this is 0, this is 0. So really all we're left with is just this one equation over here on the right. So we know whatever the final momentum of the first object is, or the first ball is, well, we know that when we add these two momenta up, they need to cancel each other out. So when we add P1 and P2 together, we know they got to equal 0. Now remember, we're trying to find the final velocity of M1 over here, mass 1. So I've left that in red for us. Well, this is going to be easy. We can just do some simple algebra and solve for V final of object 1 or ball 1. Turns out it's just a ratio between the masses, and that ratio is going to scale the velocity of the other object. We can plug in these numbers. Turns out the final velocity of the the final velocity of the first ball is negative 2 meters per second. Now let's check the sign. We have a negative 2 meters per second. Does that make sense? So let's go back to our picture. Well, according to this picture, the 30-gram ball number 1 is moving to the left. And if we think about our conventional system we've been using, this is the positive x direction, this is the negative, so it makes sense that our velocity is in the negative direction. All right. So that was, I guess, sort of an explosion. We had these particles that were sort of moving apart from each other in our system. But we need to talk about inelastic collisions and this idea of what makes an elastic versus inelastic collision. So a collision is, we've talked about it last time, when two or more objects stick together or at least interact with each other. Now, when they stick together and move with a common final velocity, this is called a perfectly inelastic collision. So you have two objects, object 1, object 2, they collide somehow, then you get this final product of object 1 plus object 2. So it's kind of like a car crash, or if you had two balls of clay and you just throw them together, then they stick together. Obviously, they don't have separate velocities anymore. They have one distinct velocity together. So you go from V1, V2 to just a V of the total object 1 plus 2. I guess we could write it as 1 plus 2 down here. All right, now that's a perfectly inelastic collision. A collision in which two or more objects bounce apart, that's an elastic collision. And the names are pretty self-explanatory. Okay, let's think about an inelastic collision here and do the math. So in a laboratory experiment, a 200-gram air track glider and a 400-gram air track glider are pushed toward each other from opposite ends of the track. Okay, and I think I have an extra video in this section on Moodle. I strongly suggest you find it and watch it because it does a really good job of actually showing this, except in the real world and not from a textbook problem. Okay, so we have these two objects pushed together, two carts on a track. They're pushed together. They both have two different momenta. So the gliders have Velcro tabs on the front and will stick together when they collide. The 200-gram glider is pushed with an initial speed of 3 meters per second. So clearly that's going to be in the positive x direction. Okay. Yep, it's pushed with 3 meters per second. The collision causes it to reverse direction at 0.4 meters per second. What is the initial speed of the 400-gram glider? Okay, so this is what we're after. We don't know what the initial speed is of the second glider. We know that its velocity is going to be in the negative x direction. But we do know after they smash together, we do know what the velocity of both of them together is. All right, so let's think about this from the law of conservation of momentum. So if I define my system to be both of these, same thing as the last problem. They're not moving up and down, so there's no external forces acting in the y direction. It's frictionless, so no forces in the x direction other than when they interact with just each other. So it's an action-reaction pair. So it sounds like external forces here, when we add them up, equal 0 newtons, which means the change in momentum is 0, which means the total momentum is constant. So I can even write that out. Big P equals some constant. We don't know what it is, but we just know it's not changing. All right, so from the law of conservation of momentum, since our system is isolated, so this is an isolated system. I cannot write. There we go, isolated system. What we start with is what we finish with. All right, so we have two objects, two different momenta. We have object one, or cart one, cart two. Okay, this is our initial. Okay, this has to equal our final. So notice what happens here in the final equation. We have to add our masses together. We have mass 1 plus mass 2. They're stuck together now. They've become one object. So you'll notice I dropped the little indices off of the final velocity as well, because it's the same for both. We don't need a v final 1, v final 2. It's going to be the same thing. Okay, so here, since we have our final masses added together, we have just one velocity we're solving for. We're good to go. Notice we just need this initial velocity of the second cart, so I've got it labeled here in red. We can do the algebra to get this variable by itself. I won't go through all of that, but essentially all you need to do is just isolate the variable. Once you've done that, plug and chunk. It's just an algebra problem. Okay, so I can just plug in what I know, what I don't know. So I do know that we got two masses here. We got the 0.2 kilogram cart, the 0.4 kilogram cart. Let's see. My final velocity, I know what it was. This is the velocity of both of them as one object. Okay, plugged that in. Looks like I know everything in my equation, and I'm good to go. So it turns out the initial velocity of the second object, whoops, I'm going to call this not a momentum, I want to call it an object, or a cart. So this is cart 2. Okay, the velocity of cart 2, the initial velocity was negative 2.1 meters per second. Now the question is, does that make sense? Well, it should, because we are going in the negative x direction, negative velocity. So that checks out. All right, so that was essentially just a quick inelastic collision. Notice there was no momentum loss or anything. It was just two objects smashed together, become one, perfectly inelastic. Now let's talk about the opposite of a collision. We'll do an explosion problem. So particles of a system moving apart from each other after a brief interaction is an explosion. We talked about this definition in the last lecture. Explosive forces are internal forces. So this could be from an expanding spring, like in the last two problems ago when we had the two balls that flew apart. That's kind of an explosion is an internal expanding spring. We also have expanding hot gases, and this is actually where we get thrust from in rocketry. And I've got the figure here. So we've got the before. Okay, here's our system. We got the fuel on board. Initial momentum is 0. So after, um, still we have the system. It's just bigger now because we're still including the rocket and the gas. We got the momentum of the rocket plus the momentum of the gas. Remember, our initial momentum was 0, which means our final momentum still has to be 0. So those two things have to cancel out. So if the gas has a negative momentum going down, well, for this to be canceled out, we need a positive momentum going up, the positive y direction. And that conservation momentum, super important in physics, very important concept. That's where we actually get momentum, and that's how rockets can actually move in space with no atmosphere. Okay, so again, these explosive forces are internal forces. If the system is isolated, just like we showed over here on the right, the momentum will be conserved. And I've already talked about this fourth bullet point in the example of rocket thrust. A rocket doesn't push against anything external. The system includes the rocket and the exhaust. So there's no external pushing. The pushing comes from those internal, like the stuff inside the box that we define our system to be. So let's think about an explosion example real quick. So we have a 10-gram bullet. It's fired from a 3-kilogram rifle with a speed of 500 meters per second. Okay, so we've got this bullet leaving. It's really hauling 500 meters per second. What is the recoil speed of the rifle? So the kickback, for those of you that shoot, you all are probably familiar with this. When you do fire a gun, you will get some kickback into your shoulder. It will bruise you if you're not careful. So let's see what this says here in the model section. So we have a simple analysis would say that the rifle exerts a force on the bullet, and the bullet by Newton's third law exerts a force on the rifle, okay, causing the rifle to recoil. However, this is a little too simple. After all, the rifle has no means by which to exert a force on the bullet. Well, that's interesting. The rifle has no means by which to exert a force on the bullet. Instead, the rifle causes a small mass of gunpowder to explode. The expanding gas then exerts forces on both the bullet and the rifle. Okay, so the idea here is it's not the bullet itself pushing back on the gun in the action-reaction pair. We're replacing the spring and the two balls with a gun, a bullet, and then the spring in there. The spring in this case is going to be the expanding gas from the explosion of the gunpowder. Okay, so now our system is essentially the bullet, the gas, and the rifle. So we have all three in there. But that's okay. We're still just looking at the things that are in motion and moving. So again, when we draw our system, you can see in the picture, we've isolated the system. It includes everything. Forces down equal forces up. So it is an isolated system. The gravity normal forces balance. And looking at this picture, the initial momentum of the system is 0. Okay, which means what we start with, what we end with in an isolated system. Right, the system is considered isolated, so the 0 has to be 0 when we finish. So we have the initial momentum of the bullet. We have the initial momentum of the rifle. Okay, all that equals 0 because they're at rest. But we know that what we start with, so this piece has to be what we end with. So that means this second piece here, the final momenta, that also when we add it together has to equal 0. Now, we want to know what the recoil speed of the rifle is. So we can do some quick algebra and actually solve for the final velocity of the rifle. Once we get that, we can plug in the values that we know, the mass of the bullet, the mass of the rifle, and then the speed of the bullet as it leaves. And it turns out we get a velocity of negative 1.7 meters per second. And this is for the velocity of the rifle. Again, we need to check and make sure, does it make sense? Well, let's look at our picture. So we've got the positive X direction in the direction of the bullet. Well, the rifle has to be the opposite directions, that be in the negative X. So yeah, looks like we're good to go. That checks out. Um, yeah, I think that's it. So this was some very simple examples of just inelastic collisions and explosions. Um, we're going to talk about in the upcoming lecture actual explosions and collisions in 2 dimensions. So we'll have stuff flying in the X direction and the Y direction. And then after that, later on, because we need some concepts about energy. So we need, I'll write that here. So we need momentum and we need energy. We need both of these to actually talk about elastic collisions. So right now we'll stick to just the inelastic and explosions. So yeah, go to the next lecture to see just 2 really comprehensive and challenging examples of momentum conservation in 2 dimensions.